When a small plane drops at 1,000 feet per minute, survivability comes down to geometry. Do you want the massive wing spar beneath you, shielding your spine, or do you want it looming overhead with 400 pounds of fuel, threatening to become the guillotine? Pilots argue paint schemes and flight feel, but the cold truth is this. Vertical impact has a winner, and it is measured in G-forces and inches of crush space, not brand loyalty. The real battle in crash physics is not high wing versus low wing. It is which design spends its last seconds saving you or sealing your fate. If your cabin stops in 1 foot, you absorb 4 Gs. If it stops in 10 feet, that extra distance can be life-saving. So where do you want the metal when you hit the ground or the water? The answer is in the numbers, and it changes everything you thought you knew about these airplanes. A vertical crash is a math problem with a single variable. How far can you stretch the stop? Deceleration equals velocity squared divided by twice the stopping distance. At 1,000 feet per minute, about 5 meters per second, if the cabin goes from flying to 0 in just 1 foot, the result is over 4 times the force of gravity. That is 4.3 G slamming through your spine, enough to break vertebrae and rupture organs. Human bodies can survive a lot, but downward forces above 15 G will snap the strongest bones. Now change only one thing, the distance. If the wreckage absorbs the blow over 10 feet instead of 1, the G load drops to less than half a G. That is a jolt you will remember, but it will not kill you. The difference is not academic. It is the entire margin between walking away and never walking again. This is why every inch of crush space matters. The best crash is the one that burns up energy in aluminum, not in your body. The Society of Automotive Engineers and NHTSA call this the short pulse problem. The shorter the stop, the higher the spike. In real-world tests, dummies that stop in 1 foot register lethal spikes. Dummies that ride out 10 feet get bruised, not buried. So when you look at a wing, a spar, a floor, or a crumple zone, you are not just seeing metal. You are seeing your own survival, measured in inches. The next time someone tells you all airplanes are the same in a crash, remember the number? 4.3 G if you stop in a foot, 0.43 G if you stop in 10. The rest of the story is geometry. A low-wing design turns the laws of physics into a survival mechanism. In a vertical crash, the wing is not just a lifting surface, it becomes a sacrificial shield. The main spar, a solid I-beam of aluminum alloy, sits directly beneath the seats. When the aircraft strikes the ground, the wing is the first structure to meet resistance. It shears, buckles, and crushes, channeling millions of joules of kinetic energy away from the cabin. This is not a gentle process. The spar deforms, the wing root tears, and the structure absorbs the blow in a controlled collapse. The floor above, reinforced by the spar, remains intact longer, buying precious milliseconds as the energy dissipates. Imagine the cabin as an egg inside a box. The wing and spar are the packing material, designed to crumple so the egg does not break. In engineering terms, the load path runs from the ground, through the wing, into the spar, and only then into the fuselage. This staged failure is what separates a bruised pilot from a fatality. The Society of Automotive Engineers calls it progressive collapse. The structure yields in a predictable order, maximizing the deceleration distance. Real-world crash data supports this. In low-wing accidents, investigators often find the wings torn away, the spar bent or snapped, but the fuselage largely intact. Dummies in test rigs record lower peak G loads when the wing absorbs the initial impact. Survivors describe a violent jolt, but the cabin does not implode. The energy is spent in metal, not bone. This geometry also sets up the next phase. As the wing absorbs the hit, the aircraft may begin to slide. The ground effect cushion, air trapped beneath the wing, can further soften the blow, reducing the vertical component of the impact. But at the core, it is the spar under your seat that acts as the final shield. In a low wing, the heaviest, strongest metal is between you and the earth. That is not an accident. That is design. A high-wing aircraft, sitting tall on its gear, carries its center of gravity higher than most pilots realize. In a Cessna 172, the loaded center of gravity rides about 30 inches above the ground, 6 to 8 inches higher than a Piper Cherokee. That difference, measured in the span of a hand, becomes lethal when the main wheels touch down in mud or soft turf. The gear sinks, the forward motion stops. But the mass perched above, the engine, the fuel, the wing, wants to keep moving. The fuselage starts to rotate around the stuck gear, like a pendulum swinging from its pivot point. The mechanics are simple. Torque equals weight times the horizontal distance from the pivot. With the center of gravity sitting higher, the moment arm grows longer. Even a modest deceleration can generate thousands of Newton-meters of rotational force. The nose pitches down, the tail rises, and the entire aircraft begins to flip. The process is quick, often less than 2 seconds from first contact to complete inversion. The pilot and passengers, now upside down, are suspended by their harnesses, staring at a crushed roof and a floor above their heads. This is not a theoretical risk. NTSB records show that high-wing trainers flip in off-field landings at a rate nearly 50% higher than their low-wing counterparts. In a soft field accident, a Cessna is 3 times as likely to end up inverted as a Piper. The difference is not just the height of the center of gravity, but the geometry of the landing gear and the narrow stance of the wheels. The wide, flat belly of a low wing can slide. The tall, narrow legs of a high wing dig in and trip the airframe. The pendulum metaphor holds, stable in flight, treacherous on the ground. Once inverted, the strongest structure, the floor, is now above you, useless. The roof, designed only to keep out rain, takes the full force of the crash. Egress becomes a race against leaking fuel and a jammed door with gravity working against every move. When the landing gear rips away in soft dirt, a low-wing aircraft doesn't tumble. It slides. The gear is designed to shear off under high loads, not to anchor the plane in place. As the wheels dig in and break free, the belly of the wing meets the ground at a shallow angle. The flat, wide surface acts like a sled, spreading the force of impact across several feet instead of focusing it on a single point. This is not just luck. It is a deliberate engineering decision. The wing roots and lower fuselage are reinforced to handle scraping and grinding, channeling energy away from the cabin. Spar. The key to surviving a soft field landing is to keep the angle shallow and the speed controlled. A low approach, with power on and the nose held up, reduces the chance of the nose wheel digging in. As the gear collapses, the aircraft settles onto its belly, the main spar taking the brunt of the slide. This keeps the center of gravity low and stable, resisting the torque that would otherwise flip the plane. The wider gear track on most low wings adds to this stability, helping the aircraft track straight even as the surface grabs at it. Control attitude. NTSB accident records show that low-wing aircraft are 3 times less likely to flip in soft field landings compared to their high-wing counterparts. The reason is simple physics: a low center of gravity, a broad stance, and a structure built to absorb sliding impacts. Pilots who keep the descent angle shallow and the nose light give themselves the best odds. The difference between walking away and being trapped upside down often comes down to inches, how far the aircraft slides before stopping, and how well the structure channels the forces away from the cabin. Statistics. A controlled belly slide doesn't just absorb energy, it preserves orientation. When the dust settles, the doors are upright, the floor is under your feet, and egress is possible. In a crash, that is the difference between a survivable accident and a rescue operation. Survivable. Water doesn't care about your intentions. It cares about displacement and density. Buoyancy governs what happens the instant an aircraft meets the surface. When a plane hits the water, the laws of buoyancy take over instantly. In a high-wing design, the wings act like pontoons, holding much of the structure above the waterline. The main spar, the fuel tanks, and much of the wing's mass sit high, which often leaves the cabin doors just inches above the rising water during the first critical seconds. This is not an accident of design. It is a direct result of how buoyant force distributes itself around the airframe. The high wing's geometry creates metacentric stability. The upward force from the displaced water acts below the center of mass, helping to keep the aircraft upright and resisting the urge to roll or capsize. Contrast this with a low wing layout. Here, the wings are submerged almost immediately, lifting the body only briefly before the fuselage begins to settle deeper. The doors, now at or below the waterline, are pressed shut by hydrostatic pressure. Even a shallow ditching can turn the cabin into a sealed compartment, trapping air and people inside. The first minute after a ditching is a race against the waterline. In a high wing, the door handles remain accessible and the sills stay dry for a handful of heartbeats. Survivors often step out onto the strut above the chaos. In a low wing, the same geometry that saves you on land now works against you. The water rises fast, the exit route narrows. The difference is measured in inches, but in those inches lies the margin between escape and entrapment. Hydrostatic pressure does not negotiate. In a low-wing aircraft, once the fuselage settles into the water, every inch of rising liquid adds weight to the door. For every foot the water climbs, the pressure climbs too, 0.43 pounds per square inch, multiplied across the entire door surface. Even a shallow submersion can pin the exit shut with hundreds of pounds of force. Panic sets in as the handle refuses to budge. One survivor of a 2018 Piper ditching described the moment, "I was screaming at the door, but it felt welded shut. Water was up to my chest. I remembered the drill, go for the window." This is the egress clock. From the instant the aircraft stops moving, the countdown begins. The cabin fills, air compresses, and pressure equalizes. Only then, sometimes after 30 seconds of chaos, does the door finally give. But most people do not wait. They break the window or force a gap, risking injury just to reach breathable air. Training changes the outcome. Pilots who practice window exits and carry simple tools like a seatbelt cutter or a window punch can buy themselves precious seconds. The checklist is brutal in its simplicity. Unbuckle, brace, break the window, and swim out. The difference between escape and entrapment is measured in seconds and preparation, not strength. In the physics of a water landing, geometry sets the challenge, but knowledge writes the ending. Fuel does not just sit quietly in a tank. It moves under pressure through a network of lines, valves, and fittings, each one a potential weak point in a crash. In high-wing aircraft like the Cessna 172, the design is almost brutally simple. Gravity does the work. Fuel tanks are built into the wings, perched above the cabin. From there, the fuel runs down through metal lines that trace the inside of the A-pillars, the vertical supports on either side of the windshield, before feeding directly into the engine. This pathway is efficient in flight, but in a crash, it is unforgiving. If a wing tears off or a line ruptures, gravity keeps pulling fuel straight down, whether the engine is running or not. The lines routed inches from the pilot's head become a direct conduit for any escaping gasoline. Low-wing aircraft like the Piper PA-28 take a different approach. Their tanks sit lower than the engine, so fuel cannot flow uphill without help. Instead, electric or engine-driven pumps pull fuel from the wings through lines that run beneath the cabin floor or along the lower fuselage. If the pumps stop, whether by switch, crash, or electrical failure, the flow stops too. The plumbing is routed away from the pilot's head, often shielded by structural members and cabin floors. In the event of a severe impact, these lines tend to crimp or break, but without gravity feeding the flow, the risk of a continuous leak is reduced. Every inch of plumbing is a trade-off. High-wing gravity feed systems are simple and reliable in flight, but in a crash, the location of the lines and the relentless pull of gravity can turn a survivable accident into a fire hazard. Low-wing pump-fed systems add mechanical complexity, but their routing and reliance on powered flow isolate the fuel more effectively when the airplane comes to rest. The difference is measured in feet of tubing, ounces of pressure, and sometimes seconds of opportunity. Fire is not a theory problem, it is a plumbing problem. In a high-wing aircraft, the fuel system is brutally simple. Gravity feeds fuel from tanks in the wing, down metal lines that run through the A-pillars, and straight into the engine. That same gravity keeps working after a crash. If a line ruptures or a fitting tears loose, fuel pours into the cockpit, even if the master switch is off. NTSB records show that high-wing gravity feed systems are linked to a higher rate of post-crash fires, nearly double the involvement seen in low-wing, pump-fed designs. The reason is as basic as water flowing downhill. Gravity does not care if you are upside down or trapped. The fuel lines are routed just inches from your face. If the tank is breached, fuel finds the lowest point, and that is often the cabin. Low-wing aircraft interrupt this chain. Their fuel sits below the engine, so it needs to be pumped up. When the pump stops, whether by switch, electrical failure, or violent impact, the flow stops too. The plumbing is routed beneath the floor, shielded by structure. In a crash, these lines tend to crimp closed, not gush. The isolation is not perfect, but it buys time. An experienced A&P technician puts it bluntly. If you are going down, kill the master and the fuel selector. That is your fire extinguisher. It is a habit that matters. The statistics back it up. In accidents where pilots cut power and fuel before impact, the chance of post-crash fire drops by more than half. The lesson is immediate. Memorize the switch locations, practice the motion. In an emergency, your hands will do what your brain has rehearsed. Gravity is relentless. Your response needs to be automatic. Every year, over 1,200 general aviation crashes in the United States force pilots to trust the physics of their airframe, often with seconds to decide. No regulation dictates where the spar sits or how the fuel flows. That choice is personal and immediate. The geometry beneath you is not theory, it is survival engineering. When impact comes, the blueprint you chose becomes your fate. Does that change how you think about your next flight?